Hi everyone, and welcome back to another array processing video. I'm Kathleen Wage. The purpose of this video is to show you how to set up and solve an optimization problem to design a narrowband beamformer with a null in the beam pattern at some angle that you choose. So to motivate this problem, let's consider the following scenario. I have some array, which I've sketched here, and I have a desired plane wave signal that's arriving at the array at some direction k sub s. For convenience here, I've assumed k sub s is equal to 0 so that it's arriving from broadside to the array. So that's our desired signal. But unfortunately, there's another signal arriving at the array from a different direction, k sub I, and that's a very loud interference. And so we may have a problem hearing our desired signal over the noise from this loud interferer. Now suppose we have a beamformer with a beam pattern that we like, some beam pattern B sub D of kz. So that I've sketched in blue here. It has side lobes. For convenience, I've assumed all those side lobes are equal height, and it has a main lobe, right, with a width that we like, right? So we have B sub D of kz, and it's got a main lobe width we like, it provides the resolution we need, and side lobes that mostly work for us, right? The problem is this interference signal, k sub I. K sub I is not located at one of the natural nulls of the beam pattern, so it will, although it will be attenuated by the beamformer since it's in a side lobe, it will not be zeroed out by the beamformer. So we would like to add a null. It would be really convenient if we could add a null at that interference direction k sub I. So we'd like to design a new beamformer that has this black dashed pattern here that looks almost like B sub D, but now it has a null at the interference direction. So that's what we'd like to do. We're starting with some beam pattern we like, B sub D of kz, and we'd like to add a null to it. So here's the optimization problem we're going to solve. We're starting with that beam pattern we like, B sub D of kz. And now here, for convenience, for the rest of the video, I'm going to work actually with B sub D of psi. Psi is simply a normalized version of the wave number. Psi is minus kz times the sensor spacing d. So that gets us into a normalized wave number, and it works out to be a standard discrete Fourier transform, where the whole transform lives between minus pi and plus pi. Okay, so this is the Fourier transform pair we have. The set of weights, I have n weights for my n sensor array. They're in WD of n, and they're a Fourier transform pair with the beam pattern B sub D of psi. So we're going to think about designing our new beam pattern, B of psi, as follows, right? We're going to say, okay, we want B of psi to be as close as we can make it to B sub D of psi. So one way we could do that is by minimizing the squared error between those two, and we'll actually integrate that error over all of the possible frequencies. So the psi variable, all the possible frequencies live between minus pi and plus pi. So we'll just minimize the normalized squared error, integrated squared error over that minus pi to plus pi region. But we'll do it subject to a constraint. So our constraint here is, this is our constraint. The constraint is that the beam pattern at psi sub I, which is the angle associated with the interferer, is equal to 0. Okay, so this is how we're going to design our new beamformer. So now we're going to try and use some Fourier transform relationships to good effect here to solve this optimization problem. So just as a reminder, the Fourier relationships we're dealing with, the weight vector we're trying to design, or the set of weights, is stored in W of n, and it has the Fourier transform, or the beam pattern, B of psi. The weights we're starting with, WD of n, has the Fourier transform, or the beam pattern, B sub D of psi. And we were looking at the difference between the beam pattern we're designing and the old desired beam pattern, right? So B of psi minus BD of psi. So we're subtracting two Fourier transforms here. And so If we do that, we know the Fourier transform is linear, so that corresponds to subtracting the weight vector. So W of n minus WD of n, right? And actually, we weren't, instead of working with this, we were actually trying to work with this integral here, 1 over 2 pi, the integral of b of psi minus bd of psi quantity squared d psi. Okay, well, we just said this is a particular Fourier transform pair, right? Well, this is looking somewhat familiar, right? If we remember Parseval's theorem, right? The integral of the magnitude squared of the Fourier transform here is equal to, in the other domain, it's equal to the sum of W of n minus WD of n squared over all n, right? So we're just making use of the Parseval's theorem relationship, right, to get this, right? This is a Fourier transform pair. We know that if we square and integrate over all time in the time domain, it's equivalent to squaring and integrating over all frequency in the frequency domain, right? And this integral is from minus pi to plus pi because we're working with discrete Fourier transforms. Okay, so we have this, right? So now, essentially what we've shown is that if we want to minimize this, it's equivalent to minimizing this. And the other thing that we have to do is figure out, well, what's going on with the constraint, right? So we also had a constraint that we were working with, and so we need to translate that as well, right? The constraint was we want b of psi sub I, the beam pattern at the angle associated with the interferer, to be equal to 0, right? And to get that, we simply recall that b of psi sub I, the beam pattern, is equivalent to the weight vector, Hermitian, times the replica vector for the interferer, right? We know that from previous videos in our previous study. So that's equivalent to saying this is equal to 0. So we can write the constraints either in terms of the beam pattern, or we can write the constraint in terms of the weights. Okay, so using Fourier properties, we've shown that minimizing this quantity, right, minimizing the squared difference in the beam pattern, the integrated squared difference in the beam pattern, is equivalent to minimizing the sum of the squared difference between the weight vectors, right? So this is the sum over all n, from n equals 0 to n minus 1 of the difference in the weight vector squared. Well, we can rewrite that in terms of a vector notation, right? We're just subtracting the vectors at each point and taking the inner product, right? So we subtract W minus WD, and then we take the inner product of that with itself, and that gets us this same summation. So our optimization problem basically reduces to minimizing W minus WD Hermitian times W minus WD, subject to the constraint that W Hermitian V sub I is equal to 0. So this is the beam pattern constraint, and this is what we're minimizing. And we used Fourier properties to get this minimization problem. So this is the minimization problem we're trying to solve, right? It's written in a nice, convenient vector form, and we can use standard constrained optimization techniques based on Lagrange multipliers to solve this problem. So I encourage you right now to pause the video and try and go through and solve this minimization problem. Okay, I hope you went through and solved the problem, and the solution, if you work it out, can be written this way. We can get the weight vector that we're looking for can be written as I minus VI Hermitian over VI Hermitian VI quantity times WD. And there we can, if we are familiar enough with linear algebra, we can recognize this as a projection matrix. It projects the weight vector WD into a subspace orthogonal to V sub I. Okay, so that is one way to view this. Another way to view it is we could do this multiplication through here, and we can write WD. All right, so we're going to take the original weight vector we started with and subtract off a component in the VI direction. And what we're doing is basically subtracting off just enough that it puts a null in the beam pattern at our desired angle. So here's the solution we've obtained. We've obtained a new weight vector that gives us a new beam pattern B of kz. That new beam pattern looks a lot like the beam pattern B sub d of kz we started with, except now it has a null in the interference direction. And we used some convenient Fourier transform relationships to define the optimization problem that we solved to get this new beamformer. So that concludes this video. Again, I'm Kathleen Wage. If you want more information, check out other videos on my YouTube channel or send me an email at k.e.wage@ieee.org. Thanks for watching.